Welcome to this short video showing how to derive the XUVAT equations. Firstly, let's talk about the elephant in the room. Why XUVAT and not SUVAT? This is because this video is aimed at WJEC physics, both GCSE and A-level, and this exam board has decided to swap the S that everyone else uses for displacement for an X. I think that's because, if you think about it, X kind of makes a lot more sense. We use X for distances and things like that a lot more often than we use S. It also means that you don't get S and you don't get speed and displacement mixed up as well. So what that means in this video is every place you see an X, if your exam board does XUVAT, then you can replace it with an S instead. Okay, right on to the actual topic then. Let's start with actually some definitions defining what these letters mean. So X is for displacement. Normally we measure that in meters. U is initial velocity, or the velocity when time equals 0, and we normally measure this in meters per second. V is final velocity, or the velocity when the time is at its maximum, or what I call time t, and again measured in meters per second. A is acceleration, or the rate of change of velocity, therefore that's measured in meters per second squared. And T is time, measured in seconds, and it's the only one of these five that is a non-vector, that is a scalar, so therefore quite useful here that we know it will be the same time for both movements in an X direction and a Y direction. On to our derivations. Let's start with our definition for acceleration. Acceleration is the rate of change of velocity, or delta V by delta divided by delta T. Using our new symbols, our initial velocity is U and our final velocity is V, so we can substitute these in for delta V, and with a bit of rearranging we get our first XUVAT equation, labelled here as 1 V equals U plus AT. Another way we can write this formula is using a graph. So if we plot a VT graph of a journey with a constant non-zero acceleration, we get a straight line like so. It starts at U when t equals 0, and it reaches V when time is its maximum. From here we know the gradient of the line is acceleration, and we can rearrange our formula to get the first equation again. Now the area underneath the VT graph is displacement, and if we look at our shape under this graph we have a trapezium. To calculate the area of a trapezium we find the mean length of its parallel sides. In this case they are U and V, and multiply it by the distance between them. In this case that's T. So this gives us our second XUVAT equation. X equals U plus V divided by 2, all times by T. From here, to get the other three, it's a case of rearranging and substituting using these two. So let's start by making both these equations T equals. We then equate these to each other. This equation is a bit of a mess, but the left-hand side is the difference of two squares. And with our final rearrangement, we get equation 3, V squared equals U squared plus 2AX. Okay, so what about equation 4 and 5? Let's this time take equations 1 and 2 again and rearrange them to make them both V equals. Again, through rearrangement and grouping like terms together, we get equation 4. X equals ut plus a half at squared. And if instead we started by both making u equals, we can get equation 5, which is sort of the forgotten XUVAT equation. X equals vt minus a half at squared. This one, not given at GCSE, not given at A level either, but does have its uses where you have a final speed and not an initial speed. So we have our 5 XUVAT equations. But why do we have 5? Well, if you look, each one is missing a term. Okay, so we've listed them in red next to each one. When you select in which one to use, work out which term you do not have, nor have to calculate from the question, and you select the appropriate equation. For more help with these equations, take a look at my video about fire, which I'll put a card up on the screen now, and thanks for watching.